Welcome to our FAULHABER Drive Time. In the last videos I explained tuning for perfect following, for small disk, for a big disk. Now let's take care about the disturbance, and therefore I'm still using the same setup here, so the MC5005 as the driver, the can open version, and the BX4 motor 3242 having the linear Hall sensors as an encoder. And now I connect a load here, so that's the motor here on your right side, and I have to tighten the coupling here. Basically that's the same motor, but here having integrated electronic, that's the MCS 3242 BX4. Both of them are connected to the same CAN, because then I can easily switch between the two of them in the Motion Manager, and both of them are connected to the same 24-volt supply. The motor, by the way, is generating a nominal torque of roughly 50 Newton meters at a nominal speed of 4,500 RPM. So let's switch to the Motion Manager and check the effects. Okay, back in the Motion Manager, but now we do have two of these drives in the device tree here. That's of course our device under test, the one that we used in the previous videos too. And here's the second one, our MCS, which I'm going to use as the disturbing machine here. Once again, identify the inertia. Shouldn't be a problem here in the setup, so run the startup method. And check the result, the inertia of the device under test, so our motor here, and here is the inertia that's been identified for the load. That's reasonable because it's the same motors, so of course the motor alone would again be a value of 30 grams centimeter square here, but we do have additional coupling, so a little more than a factor of 2 compared to the inertia of the motor would be the total inertia. That's fine. Let's transfer the parameters here. We are finished, and yeah, I can save the changes. Within the controller tuning, to see the difference, of course I can do the first step here in speed, and same single step of position, and we meanwhile know it's going to be pretty slow here, but by increasing the feed forward, applying all the feed forward values, and do once again one step, we would have pretty good following. But compensation for disturbance might not be ideal, and that's what I'm going to show. So save the parameters and leave the tool, because now I need to use two of them, so my device under test and the disturbing one, and that's better in the standard view here using the motion cockpit. First step is to run this motor. I'm using the motion cockpit. Select the profile velocity mode, enable that one, and run the motor at a constant speed here, 1000 RPM is fine. And then I directly switch to my second one here. And can directly check what's happening. So what we do see, well, let's increase the scale here, is speed and torque, and it's now minus 1000 RPM, because it's of course the inverted speed of the first motor. First motor had a plus, and now we have the minus here. Switch to cyclic synchronous torque mode, activate it, and apply disturbing torque. I will go for plus 50 and minus 50% of the nominal value of this motor, which is a numeric value of the 500 here. Well, that one would have to be a minus 500. And apply them repeatedly, and we can directly see the effect. The speed is more or less constant, but the torque is alternating here. But we don't see too much about the changing speed here, and even using the magnifying glass, the time resolution isn't really perfect for analyzing this disturbance here. Okay, to change this, what I can do is using the settings of the graphical analysis and add a trigger source here. That's what I did, the torque actual value, adding here, and the recorder would then be, well, we could either use every sample that we would get, that is a sampling of every 100 microseconds, and the trigger value, we are switching between -500 and +500, so let's use a threshold value of 0 and add a small negative delay here in order to get a few values recorded before the actual trigger event. So that's fine here, and switch back and activate the recorder and have this in a repeated mode. And now let's see the result here. So we can see there's a significant change in the speed, but the timing resolution isn't too perfect. So stop this once again and change the timing resolution a little bit. So that's in recorder settings, not every sample, but let's take every second sample only. And don't need the position, restart, and let's check what we are seeing here. Okay, here we are. I can use the ruler to actually measure what's happening here. So here is the lowest value and here's the biggest value of this speed deviation, and you can see it's close to 300. It's 290 is the deviation that we get as a maximum reaction to this disturbing torque. Then time here roughly starting at 20 milliseconds, and we are back in corridor over here at about 55 milliseconds. So this would be a reaction time of 35 milliseconds. Okay, so far the untuned case. I'm going to stop the motor here, switch back to the original one, the device under test, and stop that one too. Use the controller tuning window to adjust the gains. So let's try with a factor of 2 for the velocity loop. Yeah, seems to be fine. It's stable. And position. Well, we don't use position control here, so it doesn't really matter. But anyways, let's follow the procedure. Perfect following, and let's save the parameters here and leave the tool. And now, same, first starting the device under test here at the speed of 1000 RPM. And switch to the second one. Okay, and I can directly start the recording and switch on and apply disturbance. .500 and the -500. And apply that one here. Okay, start the recording and disable the position information here. And can stop recording once again and use the ruler to check the result here. So here's the first point, and then there's the second one here. So now we do have a deviation in speed of 170, so that's roughly 2/3 of the one that we had in the untuned case, and even the time here from starting the deviation at 20 is down to, we are back in the corridor roughly here, so that would be 20 to 25 milliseconds, so even the duration of the deviation is reduced to 2/3 of the initial one. So that's why it's important to tune and optimize tuning. It's not about following a command. The profile generator cares for these. It's to compensate disturbance. That's what I wanted to show when we have to deal with disturbances. So usually the speed loop is tuned exactly that way because we can't predict whatever disturbance we are going to have, while the built-in profile generator is dealing with perfect following. If you got any questions, don't hesitate, contact our local sales team or contact our MC support team and check back with our channel or leave a comment down below here. Thanks for watching and bye.